Oh, hi everyone. Thanks so much for showing up for your math learning. Today's topic is really the culmination of this unit, and it's where we're going to put it all together. Okay, so this is going to be like pretty rapid fire. I want to get through a lot of examples. So let's go. You got your pens out, ready to go? We are looking at rational functions where we take some rational function, some polynomial, and divide it by some other polynomial. Different orders, different things are going to happen. This is going to get crazy, everybody. Crazy. So you're going to see rational functions, and you can recognize them. We're going to see asymptotes. Discontinuities is a new idea. Okay? And we're going to be still working with intercepts. Those are our key points. We're going to recognize rational function graphs. You're going to practice polynomial over polynomial and build the graphs yourself. And we're going to sketch them. We're going to sketch rational functions. Hoo-wee! Let's go. So, they look like this. And what this is meaning is we have some m degree polynomial being divided by some n degree polynomial. And when we're working with that, we're going to see that when we have like different degrees of polynomials dividing one another, we're going to get different phenomena happening. For these larger functions, so this should say higher order functions, we're going to be combining everything that we've learned so far. We're going to see whole discontinuities and oblique asymptotes. Anyone talked about those before? Did you talk about these in grade 11? It would definitely be you will see in grade 12 this topic. Okay, so it would have been a reach ahead thing. All right, so let's take a look. If you will generate a whole inside your function if you have a factor of q of x that's common to p of x. For example, let's just generate one. F of x is equal to x squared minus 4 divided by x squared plus 4x plus 4. Okay, I'm going to use the classic classroom management strategy of picking on the people who are having cross conversations. So, Dax, yeah. What happens when I work with this function f of x?
Well, I know like a whole thing is where you like cancel it out.
Cool.
And there's like this point where you draw a hole and then it goes through and it kind of stops. It's kind of like an asymptote, but it's not an asymptote.
Yeah, it's not really an asymptote. It's just like a little gap. Yeah, cool. But with this function that I just created here, what are we going to have as we simplify that?
It's going to be difference of squares on the top.
Very good.
And then x plus 2, x plus 2 on the bottom.
Yeah, it's going to be an x plus 2 squared, or an x plus 2 times x plus 2. Very good. And you mean one... Yeah, actually, this is not a very good example because we don't end up with a whole. Usually this would give us a whole, but and we would have a whole at minus 2, but minus 2 is also an asymptote. Yeah. So, no, I was being nifty, but I didn't create one. If we had g of x here, on the other hand, that's equal to x plus 2 all squared on the top, divided by x plus 2 times x minus 2. I'm just doing the reciprocal of f of x, okay? Then here we would cancel, then we would have a whole. So then we have a whole at x equals minus 2, gives us a whole. And then if we wanted to find out where that whole is, it's actually at 0. So it's at the point minus 2, 0, we would have a whole. Okay, that's how you find the coordinate of the whole. How do I know it's at 0? Because when I substitute minus 2 into the, top of the equation there, g of x, I get 0 squared. So it's at 0, 0, 0. Notice that the denominator was also equal to 0 there, and that gives us a whole. Whenever you have a factor canceling top and bottom, you create a whole. Over here, I mistakenly thought I was creating a whole, but because I have an asymptote exactly where the hole is, it's an asymptote, it's not a whole. It's still going to be asymptotic there. Yeah?
On the test, are we going to have a question like this where there's an asymptote where the hole is? Do you want us to do g of x?
No, I'm not going to play you that way. That's like properly a trick question. I properly tricked myself when I built that example. Okay? So Yeah. So when you find these holes, the hole happens whenever you have factor cancel top and bottom like this, except in this weird case where it happens to be an asymptote as well. Wow, super cool. All right, so we're going to see some of the examples that we look at. All right, let's keep going. When we're looking at asymptotes, vertical and horizontal asymptotes are going to work in much the same way as they did yesterday. For vertical asymptotes, we're going to simplify our function first. So that's using our skills from grade 11 with rational expressions. And then, where would we expect to find vertical asymptotes? What gives us information about it? This one or this one? The denominator gives us vertical asymptotes. So for where q of x equals 0, these values give us our vertical asymptotes. X is going to give us the equation of the vertical asymptote in those cases. For whatever values of x produces 0, or the roots of q of x. That's where your vertical asymptotes are. Okay? So to find those zeros, that's going to involve factoring, long dividing, or just working with that denominator to find those roots. Okay? Investigating possible factors, all those skills. Horizontal asymptotes, on the other hand, those values that it's going to approach along the sides, those are interesting. Okay? They have to do with the degree of the functions. Okay? So on your handout, it's nicely laid out where I can look at that at the same time. Okay, so if we're thinking about up here, p of x over q of x, and we see p of x is an m degree polynomial, and q of x is an n degree polynomial, you can see if we have lower degree being divided by higher degree, then we have a horizontal asymptote at 0. Okay, let me show you an example. If we had like some mx plus b divided by some ax squared plus bx plus c, because this ax squared term, as x gets very, very large, or as x gets very, very negative, off to infinity and negative infinity, will totally overwhelm the numerator. It's always going to grow faster. If we're cubic, it's always going to grow faster than a linear function or anything lower degree. Degree always wins. Degree always beats bigger coefficients because you can always just make your x a little bit bigger. Now, I'm pausing here to say these thought experiments that you do where you say, imagine x gets very, very big. Imagine x gets very, very large, or very, very small, or very, very close to a certain number. This is pre-calculus thinking. So for those of you who are reach ahead and who are doing calculus or are going to do calculus in first year university, absolutely join me for these thought experiments. And make x become very, very large and ask yourself what happens. The squared one always overwhelms this one. Okay, so let's keep going. All right. So that's why we get an asymptote at y is equal to 0, because our denominator is getting bigger faster than the numerator is getting bigger. So we are approaching 0 in those cases. Is that a question? Oh, you're asking me to resolve a fight? Oh, I prefer settling bets. Okay. Here, if we have the same degree, top and bottom, we actually saw that yesterday, where we were dividing linear function by linear function, and we found that the leading coefficients and their ratio is what gives you your horizontal asymptote. Okay? So if we had another example here, like x cubed being divided by 8x cubed plus 2, okay? This is 1x cubed. This would have a vertical asymptote at y is equal to 1 over 8, okay? As the x cubed gets so big, it overwhelms the rest of the terms and makes them effectively nothing, right? If they don't influence stuff anymore. So we're just looking at the ratio of our leading coefficients to find those horizontal asymptotes. If you have higher degree over lower degree, like you have here, we don't have a horizontal asymptote. We may find we can create different types of asymptotes, though, and we'll look at those. Okay. So, all right, let's keep going. Any questions about that? Not really. Okay. So, x-intercepts and y-intercepts, more key points. Okay, these are our key points. If you want to set x equal to 0 to find your y-intercept, you just say f at 0 is equal to p at 0 divided by q. Oops, that's a weird way to write q. Q at 0 and evaluate. If these are in standard form, it's really easy. It's just the ratio of their constant terms. That is going to give you the point 0 and, your y-intercept. Call it c or whatever, something like that. Okay, that will give you your y-intercept. Okay, if that equals c, let's say. Okay, your x-intercept, on the other hand, you're going to set f of x equal to 0 to find your x-intercept. Right? Now, doing that is basically, in this case, we're setting p of x to be 0. If we know a fraction is equal to 0, then the numerator is equal to 0. Done, end of story, unless the denominator happens to be 0 at the same time, in which case it gets weird. All right? So we just set f of x equal to 0, which is the same thing as setting the numerator equal to 0. And then you get the point 0, and 0 is our... Sorry, no, not 0. Oh, x, we get the value of p of x at that point is your x value. Sorry, no, it's not. You usually get the x value. Blah. You get something, we'll call it d. So if x equals d, to make that true, then you'd get d0. Okay, you would get your x-intercept. Let's keep going. I'm talking too much about that. People get it. And then domain and range. We just want to describe all the possible x values and all the possible y values. Connor?
Sorry, going back to the
Yep.
thing there. You said, do we just make the top 0 or do we make the x 0? Because what if
You make the top equal to 0. That function, you're going to find where its 0 is of the numerator.
Okay.
And you'll use your factoring and your long dividing and all of those skills might be necessary to find the value the value of x that makes it equal to 0.
Okay.
Yeah.
All right.
Uh-huh.
If the top number is an integer without a variable, how would we call it an asymptote?
Oh, the value of the x-intercepts? Yeah. So there are times where will you always have these? We may not always have these because our function that's on the numerator may not have zeros. So if I have a constant function, which like let's say 4 divided by, we've already seen this, x squared plus 2x minus 7. This is absolutely a function that's never equal to 0. Okay? It's never gonna be 0 because 4 is never 0. So this never has a y value of 0 and therefore has no x-intercepts. That's fine. That can happen.
So the asymptote would be x equals 0.
Oh yeah, the asymptote here would be whatever values of this make that equal to 0. So that looks like a quadratic formula type thing for me. We can't multiply to minus 7 and add to 2. That does have roots, but they would be quadratic formula outputs. They're irrational. Okay, and this one has 2 asymptotes because I can see that it has 2 solutions in the quadratic formula, but I'm not going to evaluate it because I got lots of better examples to go. Okay, let's go. Okay, so I think you have this example on your page. Let's talk about this one. We want to examine. So what do you think we should do with f of x first, everybody? Great idea. I can common factor the top. Good work, student. I wish I had. Oh, if they were in this room, they'd have such a good mark. What about the bottom? What can I do, students who are still here? We can factor it. Very good. And what does that factor into? This is x plus 2, x plus 3. Okay, x plus 2, x plus 3. Okay, cool. All right. And then I just get out my cancel pen and cancel this and ignore it for the rest of time, right? That doesn't influence the problem whatsoever.
But when you need to do your x can equal things that
I need to do my x can't equal. So x cannot equal minus 3. But what is that when I graph it? What is it when I graph f of x?
asymptote?
This is not an asymptote.
Like a hole?
It is a hole. You need to be able to tell your holes from your asymptotes. Yes? Are you saying I should exercise more self-control and not say that joke next time? What is it?
What I was going to say is the negative 3 is your x, you plug it back in to find y.
Oh, that's really good. Yeah. Maddie, what were you going to say?
How do you know if it's a hole or an asymptote?
When you have a factor that cancels up here and down there, it's generally a hole. Generally.
But the one up there wasn't. You did up there.
I know, and I regret doing that because I was improvising.
But how did you know that was an asymptote?
Because the factor still remained on the bottom. So it's still producing a 0 on the bottom of that fraction. And when it does that, we're going to get asymptotic stuff happening. Cool, eh? Really neat exception to the rule. I wish I had introduced it after this point. All right, so now Dax said we should input that and find out what we get in our simplified function. So we have f of x is roughly equivalent, just we have a hole. F of x is equal to 2 on x plus 2. And now we're going to evaluate, because Dax said so, f at minus 3, even though we're not supposed to. It's this dirty little thing we get to do. Okay? That's equal to minus 2. I think you'll agree that's minus 2. You all see it? No one needs to see the next step? The minus 3 plus 2 is indeed minus 1, and 2 divided by minus 1 is minus 2. I skip all these steps because that's my way of saying I see you. And I see that you know how fraction work. So I just skip the steps. Okay, so we have a hole at minus 3 minus 2. Cool. And now let's also go a little deeper with f of x. Where is f of x? Let's find the key points now. How do we find our key points for f of x? So I want to find my key points. So find me the x-intercepts and the y-intercepts. First of all, what's the x-intercept for f of x? Sorry? Negative 2 is the x-intercept?
Isn't it
Negative 2 over 3.
Do we need to bring the x plus 3 back? No.
For what values of x is f of x equal to 0? Remember, f of x equals 0 when you have an x-intercept. So what values of x make 2 equal to 0? Oh, he's getting mad. You know I'm not actually mad, right? Okay, yeah. So if I set f of, really? Yeah, I'm that good of an actor? You thought I was being for reals? Yeah. F of x equals 0? How do I make 2 equal 0? Someone tell me.
Which two? The bottom two or the top one?
Huh? Huh? What?
Which two?
Someone tell me that no value of x makes 2 equal 0. Someone tell me there's no x-intercept here. There's no x-intercept. What's our horizontal asymptote? Our horizontal, this is the horizontal. Okay, let's wind back here. When m is less than n, when this is lower degree than that, we have an asymptote at y is equal to 0. That's our horizontal asymptote, y is equal to 0. You said that? Oh, you're back in the club. I'll let you back in the club, okay? I'm not going to suspend you. The rest of the students are suspended starting tomorrow. Okay, so we have a horizontal asymptote at y equals 0. Important stuff. Constant over a linear function. Linear function, higher degree. Linear function over a quadratic. Quadratic, higher degree. Horizontal asymptote at y is equal to 0. No x-intercepts, folks. No x-intercepts. Okay? They don't exist. All right. So now, how about y-intercepts? How do we find y-intercepts? Thank you. We set x equal to 0. F at 0 equals 2 over 0 plus 2. Someone evaluate this and tell me what it is. No Jeopardy music. Dax? 1. I agree. 2 divided by 2 is 1. So we have this y-intercept, 0, 1. Cool. We're getting all this data by doing our different algebraic tests. Very cool. Now we have our horizontal asymptote, y is equal to 0. Find me our vertical asymptote. What's our vertical asymptote? Very good. Someone's, who was that? Was that Charlie? It was Yusuf. Oh, good. Yusuf told me to set the denominator equal to 0 to find out what values x could not be. So if x plus 2 is not able to be 0, then that means x is not able to be minus 2, and that's good. We have our two restrictions, but they're very different. This one gives us a whole. This one gives us an asymptote. All right? So now we might test our asymptotic behavior. I don't really want to do that. I just want to pop over and check the Desmos. So we're going to go in here. We're going to find this one that's on. This is freely available on the D2L, and you can click and find the Desmos graphs for all of these slides. Here it is. Check it out, everybody. There is our whole at minus 3, minus 2. That's weird. Is this really the same one? Yes. So over 2 over x plus 2. Put minus 3 there. X is minus 3. That's not minus 3. What? Is that what we found? We have a whole at minus 3, minus 2. I don't know why I was doubting us. We have it there. We have our asymptotes. We test our asymptotic behaviors, and we produce that sketch. Okay? So we're going to be moving a little quickly just to like, move on to a new example, but know that all the examples are in here. You're expected to be able to sketch all of them and be able to do that. I'm happy to walk through a few examples step by step with you, but let's keep going. Okay, so do I have this one on the handout? I think I skipped that one. Yeah? Yeah. The limitation value. We do have this one on the handout. Okay. So what do we do here? What's our first thing that you're going to do so that you can investigate this? Let's simplify it. What am I going to write as the numerator? Absolutely do your rough work in another place if you want to factor that step by step. But if you can factor it in your head, that's great. I am going to do my rough work for the bottom in another place. What rough work do you think I'm going to do with that? And no, I don't need quadratic formula. Huh? Sorry? I'm going to take out a common factor. What common factor do you suppose I'm going to take out of the bottom? Let's do it. So I'm going to write that as negative 1 times x squared minus 6x plus 8. And then I'm going to carefully factor this. There. That pretty good? And then I could just put it in that way. Or I could distribute that in and call it 4 minus x, but I think I'll keep it that way. Okay, so then I'm going to write it as x minus 2 times x minus 4, but we are negative there. Okay? Then I get out my cancel pen, and I do this. I have a whole at what flavor of 2? Yeah, a whole is at x is equal to 2. Okay, so now, what's the y value of my whole? Emma, do you have it? The y value of my hole? You looked excited. Charlie's got us. Charlie said 3.
Yes.
What type of 3, Charlie?
Positive.
That just worked perfectly. If you put in 2, right, you want to input 2 into this function and find out. What's 2 minus 4?
-2.
What's 2 plus 4 on the top?
6.
What's 6 divided by -2?
-3.
There we go. We got it. So we've got a hole at 2 minus 3. We have a little hole in our graph.
What about the negative in front?
Oh, but it's negative in front. Who wants to mark it? Who wants to mark my error?
Me. I do.
Go for it, Charlie. You were right. I was wrong. Yeah. So go up. Add number 3 to my tallies up there. Yeah. All right. That's great. Bonus marks for Charlie. Okay, I wasn't counting this minus. It was too far away in my mind to see it. So be very careful. I actually had heebie-jeebies as I canceled it and thought, I don't want to lose that one. But I did. Oh, that's good. Okay, so we have f of x equals x plus 4 over 4 minus x. There's our function. I could write it that way. I can distribute this negative in there if I want. It's kind of my preference. And then turn them around. Or I could say minus x minus 4 is fine. Whatever. Okay. Now with this, we investigate to get our key points and all that. Can this one have x-intercepts? Can this one have an x-intercept? I really zinged you all last time where it couldn't have an x-intercept. Can this one? How do we find x-intercepts, everyone? Set f of x equal to 0. Good. So for y-intercept, you set f of x equal to 0, which is the same thing as setting the numerator equal to 0.
So
I was bored before.
But wait, can x be -4? Yeah, it can, because you're allowed to divide by 8. Because we're minus 4 down there. So don't get fooled. Don't get fooled. This is designed to fool you. Don't. Okay, so we have a y-intercept at -4, 0. That was hard work to find. So highlight it. Don't lose those points on your work, okay? Let's find x-intercepts. Sorry, no, that's our x-intercept. I'm sorry, it's not our y-intercept. That doesn't count as an error. I'm not putting up double digits today in errors, okay? That's just I misspoke. Y-intercept, we're going to set what to 0? So evaluate f at 0 equals 0 plus 4 over 4 minus 0. So where's our y-intercept? 0, 1. Good. Highlight it. We need that point to create a good sketch. Where are our asymptotes, if any? Horizontal asymptote. Where is it? Our horizontal asymptote we get as a ratio of the what?
do we see that was our y-intercept?
Here's our y-intercept
my
there.
bad. Yeah, my bad. I had
Yeah,
a brain fart.
there's our y-intercept there. But how do we find our horizontal asymptote? Look on your sheet. It tells you. What flavor of 1, Kunal? They're both degree, 1 on top after we simplify. But the coefficients, yeah. So the coefficient here and the coefficient here give us our our horizontal asymptote. So we have 1 over minus 1 equals y equals -1 is our horizontal asymptote. We had to work hard to find it, so highlight it. I don't know why it does that thing where it highlights from the bottom of the page. It's super weird. It only does it sometimes. It's still doing it. I don't care. Okay. All right, and then our vertical asymptote happens where? At what value? You said it? No. Yeah, positive 4. You set your denominator equal to 0, which it can't be. So if 4 minus x equals 0, that means x equals 4. And so then we have a vertical asymptote at x equals 4. Okay, that's our vertical asymptote. And then we test our asymptotic behavior. Allow x to become very, very large or very, very small to check its behavior around the horizontal asymptote. Allow x to become very, very close to 4 from either side to check the behavior around the vertical asymptote. Let's take a look at the sketch. Not the sketch, the perfect graph. Boop. Okay, there's our asymptote at -1 and 4. And there's our hole at 2, 3. Just like Charlie predicted. Charlie, give yourself a pat on the back. All right, good work, everybody. Let's keep going. What example do I have next on the sheet? Oh, look, a cubic. Oh, I'm so excited. Something juicy. You have this one on the sheet?
No, we should skip it.
We should skip it? Oh, man, it's juicy. All right, fine, I'm going to do it. Okay, I'm just going to erase it. So, I factor the bottom. I test different factors, so I need to look at 1. 1 works. X can be 1, and this is equal to 0. So I'm going to divide x minus 1 into 3x cubed plus x squared minus 8x plus 4. I thought I would speed run this, but I'm happy I'm doing this example really quickly for you because some people need to review your long division. Either you have like niggling errors and it makes it really frustrating for you, or some people still can't long divide. You absolutely need to take a pause and go back and learn to long divide if that's something you need to work on. Okay, so we have 3x squared. We multiply that through to get 3x cubed minus 3x squared. Put it in brackets and remember you're subtracting. Then, one thing I saw on a thumbnail that Google suggested to me was a teacher did that to show that that goes away. And I liked it. And then you do x squared minus 3x squared. That's 4x squared. Some people aren't taking this down correctly. Okay? You have to do that operation together. And then I look at what do I need to multiply x by to get a 4x squared? Well, that would be plus 4x. And then I multiply to get 4x squared minus 4x. And I bring this minus 8x down. And I subtract here. And this cancels. And I get nothing there. And I get minus 4x. So I'm minus 4x there. Because negative 8x plus 4x gives me minus 4x. Bring down my plus 4. I notice that I get a remainder 0 when I multiply by minus 4 here. So I have now f of x. Maybe I write down some intermediate step as x minus 1 over x minus 1. Look, another whole, everybody. Times 3x squared plus 4x minus 4. Will that one factor? Yeah, I think it does. Yeah, you can multiply to negative 12 and add to positive 4. It's 6 and minus 2. So that one will keep factoring, and we would keep factoring to investigate it further, but we're not going to. We're just going to peep at the graph and see, what do you expect to find at x is equal to 1? What are we going to find at x is equal to 1 when we look at this one's graph? A hole. Good. And what will the y value of that hole be? Look at the function. It'll be like 0-ish. Yeah, 0-ish. Yeah, it's a 0 on the bottom too. But it's going to be, oh wait, no, it's going to be 1 on top. No, it's going to be 1 on top. So actually we're going to look at what 1 gives us in there. So f of x could be written as this. This is what we would have. F of x is equal to 1 over 3x squared plus 4x minus 4. We feed this the value 1, and we get 1/3. So we're going to find that that hole is at 1/3. Cool, eh? So it's not at 0, because y also, the denominator also goes to 0 at that same point, but that cancels out. So let's take a look. How did I get 1/3? I just input. This is 3 plus 4 minus 4. I put x as 1 in there. Yeah, I put x as 1, and that gives me 3. So the denominator is 3. Okay, so it's this one. There it is. Hey! No more mistakes for me today. That's me knocking on wood. Okay, all right, so and then we see there's 2 asymptotes. We have those 2 asymptotes. We already knew that because we knew it would factor into 2 factors. And we have a horizontal asymptote at 0 because we have smaller order over larger order. No surprises here, everyone. Let's keep going. Okay, let's keep going. So we have our next one, this one. What does that factor into?
X plus 4, X plus 3.
X plus 4, X plus 3. Okay, cool.
We get a hole at -3.
So we have a hole at -3, and what's the y value of the hole?
Is it 1?
1, good. And what shape do you expect the graph of this function to have when we look at it? We have larger order over smaller order, quadratic over linear function, and the linear factor cancels away perfectly.
So should it just be a line?
Be like the
Very good. Yeah, we're going to get a line, and the line is going to look an awful lot like x plus 4. Let's go ahead and take a look at it. So boop, there it is. And there's our hole at -3, 1. Ding, 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 ding. Very good. Very good, everybody. Any questions about this one? Where are the asymptotes? And it ain't got no asymptotes. That's good. That's right. Because there's no denominator left after we've taken that hole out. And there's no way to make the top... Oh, wait. No, it's equal to, like, yeah, no, it's just, there's no... It's higher order over lower order, so there's no horizontal asymptote. That's all. Okay. How about this one? What did you find with this one?
Yes. And then difference is squares in the order.
Does this one have any holes?
No.
No holes here in that one. Does it have any vertical asymptotes? Does it have any vertical asymptotes, this one? Yes, vertical asymptotes are at x is equal to plus or minus 2. Very good. That's what that makes that 0. How about horizontal asymptotes? Oh yeah, someone said 1/1. Good, because we just look at the coefficients here and here. And the coefficients of our leading terms is 1/1. So our horizontal asymptote is absolutely at y is equal to 1/1, just 1. Good. So we found those. You would investigate your asymptotic behavior to get more data out of that. But then, what's our x-intercept? How do we find x-intercepts again? X-intercepts happen when y is equal to what? 0. So I set what to 0? The whole thing, f of x equal to 0. Good. So what values give f at x equal to 0? What values of x make that happen?
3, -1.
Fantastic. So x-intercepts happen at -1, 0, and 3, 0. Connor knew that because he knew that those values would make that equal to 0 in the numerator. Very good. How about y-intercept? How do we find the y-intercept here? Yeah, set x equal to 0. Good. Where's the easiest spot to set x equal to 0? I would say the original function. Set x to 0 in the original function is easier than setting it equal to 0 in the factored function.
So So just get through.
The factored function, we have a whole bunch of multiplication to do. In the original function, I just do this. Minus 3 over minus 4. Because I'm just multiplying all those things by 0. 0 to the power anything is 0, and anything times 0 is 0. So all those things add up to 0. So my y-intercept is at 0, 3/4. Okay? And then we investigate asymptotic behavior. I just don't have the patience to do that right now, but we'll look at it, okay? And so let's look at it in Desmos. Okay, so we have, boop, turn that off, boop, turn this on. All right, so here are our y-intercepts, 3, 0, minus 1, 0. Cool, look at that. The asymptotic behavior is a little different than what we've seen before. So I kind of regret that I chose not to look at our asymptotic behavior. Okay? Our asymptotes are exactly where we thought they'd be. All right? We have our y-intercept at 3/4. We have our x-intercepts where we thought they'd be, and our horizontal asymptotes, vertical asymptotes are at 2 and negative 2. Okay? So when we test, you just go ahead and you input into your function like very big values of x and very small values of x, and you find your horizontal asymptote behavior. And then let's just test around one of them. Let's test around 2. Okay, so I'm just going to test around 2. So I'm going to say here, this one, f of x equals x squared minus 2x minus 3 over x squared minus 4. I would rather substitute in that than substitute in that. They are algebraically equivalent, so you get to choose what you work with. So let's set f equal to 2.01 and see what we get. We get 2.01 squared minus 2 times 2.01 minus 3, all divided by 2.01 squared minus 4. That's a calculator problem if I ever seen one. Okay. Maybe if you were asked to do this on a non-calculator, you could test some nifty values or something, but who cares? 2.01 squared minus 2 times 2.01 minus 3 equals, that's my numerator. Okay, divided by, put your denominator in brackets, 2.01, square it, minus 4, and the bracket, that's my denominator, equals very big negative number. So on my table I have as x goes to, f of x goes to, and I have as x goes to 2 on the positive side, f of x goes to negative infinity. Okay, that's how your tests go. And then as I have x go to 2 on the positive side, you see it goes down to negative infinity. See there. But then we have the opposite behavior on the other side of 2. And you would do the test in exactly the same way and show exactly the same thing. And this shows, just because you know a few points doesn't mean you shouldn't test your behavior, okay? We have x going down to negative infinity and then up to positive infinity there. All right? Cool, cool, cool. Okay, now, okay, at this point, we got to tune back in. And we got to say we have 4 minutes left. My goodness. We might get to oblique asymptotes tomorrow. I think now is the time to say this is lesson 2.4 and tomorrow is lesson 2.45. And then we will just cover oblique asymptotes. So, oblique asymptotes here. This is a new idea that we are going to see here, and we are going to go beyond. We are going to be masters of oblique asymptotes because we are going to be masters of long division. All right, and we are going to investigate this tomorrow. Okay, who's having fun yet? Is having fun? Yeah, this is kind of cool. I see some things are starting to click. Yeah, this is a neat topic. It's super cool and fun. Here's how you practice. Throw a function on top of another function in Desmos and then hide it from yourself. Even better, like make them factorable and share a factor or not share a factor or be higher order, lower order, higher order, lower order, and practice and graph them. Or graph the examples. Graph the ones that are in your handout, do some practice today, and come to me with questions tomorrow. Bye for now, everyone. If I was throwing shade at you today, I just hope you know that's only for dramatic effect. Bye for now, everybody.